Welcome to the Math Record. Today we'll be covering power series. This video will cover part 4 of chapter 4 in our calculus class. Okay, let's begin. So what is a power series? A power series is basically just a sum of an infinite amount of terms. A power series is usually in the form of the summation from k is equal to 0. So it begins at 0 and it goes to infinity. And we have an equation of a subscript k, so it's just an equation of k. It's just an equation times an x minus a constant to the power of k. So how to interpret this is that we start from 0 and it goes to infinity, so it has an infinite amount of terms, and you have to take the sum of it because it's a series, right? And a k, a subscript k, is just an equation, so it's just a general equation that we want to plug in. And then x minus c, this tells us where we need to position the graph. So do we want to start c at, we want to center the equation at 1, at 2, at 3. So that's basically what that is. You don't have to understand why that works. It's just that if you follow the formula, it will make sense. And then k is our exponent, which we want to raise to it because it's a sum of terms. It's kind of like a polynomial. So the follow-up question is, how do we determine if a power series converges or diverges? For power series, this is kind of simple. The procedure is just kind of long. So to solve if we could converge this, is that there is a concept called the radius or interval of convergence, which is a range of numbers where these series converges. So to try to understand this, let's try to use an example. So let's say we have a summation from k is equal to 0 to infinity, right? And we have an equation of x to the power of 5k divided by k. Okay, so this is our equation. This is our summation. So the general idea of how to do this is that you first use the ratio test. So the ratio test is that you take the limit as your variable, which is k, as that approaches infinity, and you take the absolute value, and you take the first. So the general idea is the term of n plus 1, n subscript n plus 1 is divided by the a subscript n is equal to like some kind of number, right? So the limit as the next term divided by the previous term, that has to be less than 1. And that's how we find the range of convergence. So for this specific example, we just have to find the limit as k approaches infinity of the absolute value. So the next term, all you have to do is just plug in k plus 1 in here. So when you plug in k plus 1, we have x to the power of 5. So k becomes k plus 1. So parentheses k plus 1 divided by k plus 1. Divide all over, right? So that's just a n plus 1, and we need a of n. So that's just our original equation. So we just plug in a to the power of 5k divided by k, right? And we take the absolute value of this entire thing. And that has to be less than 1. This entire thing has to be less than 1. So let's kind of simplify this. So the limit as k approaches infinity, right? So x to the power of 5k plus 1, that just simplifies to x to the power of 5k plus 5, right? So let's kind of write this a little neater. 5k plus 5 divided by k plus 1. And when you're dividing by something, you're just multiplying by this reciprocal. So it's just multiplied by k all over x to the power of 5k, right? So then you divide these two numbers out. So all you have left is just, sorry, I forgot the absolute value. So let's kind of add that in. So you have the limit as k approaches infinity as the absolute value of x to the power of 5, right, times k divided by k plus 1. And all of that has to be less than 1 still, right? So as the limit as k approaches infinity, right, x is a variable, so you can't simplify that just yet. But as k approaches infinity, that means it becomes a really big number on the top and becomes a really big number on the bottom, right? That means these two numbers, since k becomes such a big number, this 1 would not matter at all because it's too small, right? So let's say k is like a million, right? Who cares if k plus 1 adds to like a million and one? It doesn't matter because a million divided by a million and one would just be somewhere around 1, right? So it kind of doesn't matter. So since as limit as k approaches infinity, it's just k divided by k plus 1 is just 1, which is just a basic idea of limits. So that means the absolute value. So if you simplify this, it's just the x to the power of 5 absolute value is less than 1, right? Because as you take the limit as k approaches infinity, that means all you're left with is just x to the power of 5 times a really big number divided by a really big number, right? So since the top number, the numerator, is multiplied by x to the power of 5, then all you have remaining is just x to the power of 5, right? So now we're simplified to this. So the absolute value of x to the power of 5 has to be less than 1, which is just the ratio test. This is just basically the ratio test that I've been doing the entire time. So the first step is the ratio test, okay, which is just this separate process. So now all we have to do is find the lowest x value and the largest x value. So the lowest is x is equal to -1, right? Because if you plug in -1 here, -1 to the power of 5 is -1. Absolute value of -1 is 1, so which is less than 1. So that works. It isn't less than 1, but it's just an endpoint, right? So the next term is x is equal. So the highest value now is x equal 1. So these are your boundaries. You know it's x is equal to 1 because 1 to the power of 5 is 1. Absolute value of 1 is 1, which is less than 1. So it's at the boundary point. So we know that the summation of k is equal to 0 to infinity, the endpoints of where it could converge, possibly converge, is from -1 to 1. Okay, so let's kind of delete all this. And that's basically the first part. The first part, we use the ratio test to find out that x has to be from -1 to 1, where it could possibly converge. So now we have to do, which is another step. The next step is basically plug in -1, the two endpoints, so we know which one could be satisfying the series, the power series. Sorry about that. So we check both of them because maybe one of the endpoints could become a converging while the other ones cannot, or both of them could, or both of them cannot. So all we have to do is just plug it in, right? So when when x is equal to -1, we have the summation as k is equal to 0 to infinity. So when x is equal to -1, we have -1 to the power of 5k divided by k. And that just simplifies to -1 to the power of k divided by k, right? So if you look at this equation, this just looks like -1 to the power of k times 1 over k, right? This is this equivalent equation. And what does this look like? This looks like an alternating series, which I covered in our past video. And a alternating series converges if this equation, the limit of as k approaches infinity of 1 over k is equal to 0. And does that condition satisfy? Well, it does, right? Because as k becomes a really big number, 1 over k becomes really small and it approaches 0. So this satisfies. And also, um, 1 over k has been non-increasing. So is it non-increasing? Well, you could just plug in some values, right? So if k is equal to 1, that's 1. When k is equal to 2, that's 1 divided by 2, that's 1 half. When k is equal to 3, that's 1 over 3. When k is equal to 4, it's 1 over 4. As you see, it's 1 to 1 half to 1 third to 1 fourth. It's decreasing and decreasing every single time. So it's non-increasing. So this condition is satisfied. So this tells us that when x is equal to, let me delete the rest of this. When x is equal to -1, then it converges. So the inequality now is less than or equal to -1, because when it's -1, 2, it's going to be converging. Okay, so that checks one of the endpoints. That checks x is equal to -1. Now let's check x is equal to 1 now. So when x is equal to 1, summation, x is equal to 0, infinity. And then when you plug in x is equal to 1 here, is 1 to the power of 5k divided by k. 1 to the power of any number is just 1, so that's just 1 over k. And we know for sure that this is not going to converge. This is going to diverge. Why? Because this is something that we covered before called the p-series in a earlier video, which we said that if 1 divided by like some kind of equation, x, right, to power p, where is p will this equation will only converge if p is greater than 1. Since p is less than is exactly 1 right here, right? This is just substitute the k is equal to x, right? Then the exponent is 1. Since the exponent is 1, that means this is going to diverge. Because if you want it to converge, it has to be greater than 1. So we know that for sure that this diverge. So that means this is correct. It's just less than 1. So our interval of convergence, which we refer to as the range of where an equation would converge, is just this. So if you plug in any numbers from -1 to 1, um, then it's going to converge. Not including the 1, but you are including the -1. So you include something like x is equal to like -0.95, right? It's between this interval. Then if x is equal to this number, then this equation would converge. And that's the general idea of the power series. So an additional thing to cover, sorry about that, is that this is called the interval of convergence, which I said earlier, of convergence. To This is different from something called the radius of convergence. The radius of convergence is basically just a number. So how to find it is basically take your upper bound, which is 1, minus your lower bound, which is -1, so minus -1, and then you divide that by 2. So 1 minus -1, that's 2. 2 divided by 2 is 1. So your radius is convergence is 1. So the reason they call this the radius and convergence is that let's kind of graph this out, right? In a number line, right? So we have -1, and we have 0, and we have 1, right? So we're centering this around 0, and then the radius is convergence is from 0 to -1 and 0 to 1, right? So sorry about that. From 0 to 1. So the distance from 0 from both of them is 1 unit away, right? And that's why it's called the radius convergence, because it's like the same distance away. And that's why you could just have the upper bound minus the lower bound and divide by 2, because that's basically where the equal distance is. And that's why in our general formula, which we have for power series from the summation of k is equal to 0 to infinity of a subscript k, which is your equation, times x minus your constant to the power of k, this constant tells us where your center is. So remember where we draw the line, which is -1, 0 to 1. Our center is at 0 because it's just 1 unit away from both sides. That's where the center is. Well, if you look in our equation, oops, sorry. If we look at our equation, where is our x? Our x is right here, right? So if you kind of write this out differently, it's basically the same as x minus 0 to the power of 5k divided by k, right? Our center of convergence is 0, which is c, right? So this tells us that our thing starts at 0 and goes to -1 and 1. So if you know where your center is and what your radial convergence is, you basically just find your interval of convergence without doing all the math. But it's usually such a rare case that, but in, but that's usually a rare case, and all you had to, but the general procedure you're going to be doing is that you're going to have to use the ratio test, and then you have to test your endpoints. So it's a two-step procedure. Use the ratio test, simplify that, and then find your interval of convergence, and then you test both your endpoints to see which one fits the test, fits a convergence. And that's usually one of them would fit a alternating series test, usually. So to understand this, let's try another example, right? So let's do it again. So let's say we have the summation from k is equal to 0 as we approach infinity, and we have negative 1 to the power of k times, like, let's say 2x minus 5, right? So now our interval converges at 5. It's the power of k all over k, right? So the first thing we had to do, we had to use the ratio test. Okay, so first thing we had to do, ratio test. So we had to limit as k approaches infinity, and our ratio test is negative 1, power of k plus 1, times 2x minus 5 to the power of k plus 1, divided by k plus 1, right? So that's our top equation. So let's kind of make this a little bigger, this absolute value a little bigger. And that's all divided by, so all that is divided by our original equation, which is negative 1 to the power of k times 2x minus 5 power of x, power of k divided by k. So what can we cancel out? So we could cancel out this number, and that's just left with negative 1 to power 1, which is just negative 1. So I'm just going to write negative 1 on top so we remember. And we could just take this one out. So this would just be less than 2x minus 5, right? So if we are simplifying this, the limit, right, and this has to be less than 1. As k approaches infinity, we have negative 1 times 2x minus 5, and then it's divided by k plus 1, and then it's also divided by 1 over k minus 1, right? So that's multiplied by k and divided by k plus 1, right? It just seems kind of messy. If you want to write this out on paper and do it yourself, then it should simplify out to this. Okay? So as k approaches infinity, right? This is just the same case of what we did with our previous example. As it approaches infinity, k becomes a really big number. K on the bottom also becomes such a big number that this 1 doesn't matter. Then as this approaches infinity, then all this simplifies to is just the limit. Oh, sorry. The limit as k. I'm sorry. Sorry about that. We already took the limit. So the limit as k approaches infinity, the k divided by this k, all you have left is that negative 1 times 2x minus 5. Absolute value is less than 1. Okay, let's kind of delete all this so then we get a little bit more room to do more math. Okay, and delete, delete, delete. I think I deleted a k. Oh, yes, I forgot the k. Okay, so put the k here, right? And I'll rewrite that on top. So we have negative 1 times 2x minus 5, absolute, parentheses, absolute value is be less than 1. Okay, so I'll delete this. So when, so what's the lowest possible value? The lowest possible value is negative 1, right? So 2x minus 1 is equal to negative 1. So then 2x minus 1 is equal to 1, right? Because divide by -1 on both sides is just 1. So then your x here, your 2x is equal to 6, so x is equal to 3. So if you want to check if that works, just plug in x is equal to 3 here. So that's 2 times 3 is 6, 6 minus 1 is 5. I mean 6 minus 5 is 1. 1 times -1 is -1. Absolute value of 1 is 1. Okay, so that works. So then to find the upper value, to find the other value, -1, 2x minus 5. Absolute value is equal to 1 now. So -1 divided by -1 is -1. Oops, sorry. 2x minus 5 is equal to -1. So 2x is equal to 4, right? 5 plus -1 is 4, and x is equal to 2. Okay, so their interval is from 2 is less than x is less than 3, right? So based on our ratio test, we know that our interval of convergence is from 2 to x to 3. So that's our first part. Now we just need to modify to make it correct, right? So this isn't like this is an interval of convergence, but it's not the actual integral convergence that we need. So let's move this up. Okay. So the second step, all we have to do is plug these numbers back in. So we just need to plug in a 2, right? So the summation from k is equal to 0 to infinity, -1 to the power of k, times when x is equal to 2. When x is equal to 2, that's 2 times 2 is 4. 4 minus 5 is -1, so that's just -1 to the power of k, divided by k, right? So let's think about this. If k is equal to 0, right, then -1 to the power of 0 is 1, -1 to the power of 0 is 1, so 1 times 1 is 1. And 1 divided by 0, that's undefined. So let's plug in a different number. So let's say k is equal to 1. -1 to the power of 1 is -1, times -1 to the power of 1 is -1, so -1 times -1 is 1. If you plug in k is equal to 2, that's a positive times a positive is positive. So this general idea is that if -1 to the power of k times -1 to the power of k, all that is just going to lead to is just going to be a 1, right? And that's just 1 over k, right? So that tells us that our simplified version, 1 over k, this diverges, which is what we said in our previous example, right? Because since 1 over k, that's just the p series again, which is that 1 over x to the p, where p has to be greater than 1 for it to converge. Since p is exactly 1, since the exponent right here is 1, then it's gonna diverge. Okay? So this is when x is equal to 2. Let's plug in when x is equal to 3. So k is approaching infinity. Then we have -1 to the power of k times when x is equal to 3. So 2 times 3 is 6. 6 minus 5 is 1. So 1 to the power of k divided by k. Since 1 to the power of k is just 1, it doesn't matter. So all you have to write that as is the summation from k is equal to 0 to infinity of -1 to the power of k divided by k. Okay, now, actually, let's kind of make this a little nicer to understand. -1 to the power of k divided by k. Okay, what does this look like? Well, it looks like an alternating series, right? If you ever see a -1 to the power of k, you might want to check if it's alternating. But you can't always assume it's an alternating series because look at this, we have two -1s, but it's not alternating. It's not alternating because this is negative and this is negative. And since these are the same exponents, that means it's always going to be a negative times a negative, which is going to make a positive, or a positive times a positive, which equals a positive, right? So that's never going to work. So the top is always going to be positive, so it's never going to be alternating. But for this equation, it's always going to be alternating, right? Because it goes from -1 and to the power of k, and that's the only -1 to the power of k. So it's always going to be negative, positive, negative, positive, negative, positive, right? So it's always going to be alternating. So since this is alternating, we just have to check the two conditions for alternating series, which is that this equation, the limit is 0. So you don't include the -1 to the power of k, so it's just 1 over k. So is the limit as k approaches, I'll just write out the entire thing. Is the limit as k approaches infinity of 1 over k 0? It is, right? It's just because as k approaches a really big number, that means 1 divided by a really big number is a small number, and it gets smaller and smaller, so it's 0. Number 2, so the second condition is that k is non-increasing. Is k non-increasing? Non-increase. Well, it is non-increasing, right? Because it's 1 over k. So you plug in some numbers. If k is equal to 1, that's just 1. When k is equal to 2, that's 1 half. When k is equal to 3, that's 1/3. When k is equal to 4, that's 1/4, right? So it's getting smaller and smaller every single time, so it's non-increasing. So it checks this condition. Since it works for this condition, that means when it's equal to -3, it's when it's equal to 3, it's going to be converging because it passes the alternating series convergence test. So a absolute you put a line here, so so now your new interval convergence is from 2 to 3, but it includes 3, right? So you plug in any numbers from 2 to 3, but it does not include 2 and it includes 3. All those numbers, those are gonna, when you plug into x, it makes this power series converging, a converging power series. So now the follow-up is, what is this radius of convergence? Well, what we could do is the same thing. So 3 minus 2 divided by 2, right? Upper minus lower divided by 2. So that's 1/1/2. So your radius of convergence is 1/2. Okay. And that basically covers our second example. Another concept we will tackle is, how do we represent functions as power series? To do this, we need to know the infinite geometric series, which I introduced in part 2 of chapter 4. So the general idea is that we're going to have the limit, we have the summation as k is equal to 0 to infinity, and it's in the form it's in the form x to the power of k. This summation would equal to 1 over 1 minus x if x is between -1 and 1. So this is the idea of the infinite geometric series. Geometric series, right? So we have the summation of when k is equal to 0 and when k goes up to infinity. So we have an infinite amount of terms, so it's infinite geometric, right? As x, some kind of number, is raised to a power because k is equal to 0. So k's group goes from 0, 1, 2, 3, 4 to all the way into infinity. You add all those numbers up, is the final sum is going to be equal to 1 divided by 1 minus x. If that x is between -1 and 1. Not 1, not it cannot be -1 or 1. It has to be between -1 and 1. So this is the formula that we need to know. So to represent functions as power series, let's kind of understand this using an example. So let's say we have our function, which is f of x, and that's equal to 5 divided by 1 minus 5 x to the power 5. So the first thing we want to do, since we want to put it in the form 1 minus x, because that's equal to the summation as k is equal to 0 to infinity of, um, sorry, of x to the power of k, right? All we have to do is just get this equation to that form. So we have to take out the 5. So we have 5 times 1 over 1 minus 5x to the power of 5. Okay. Oops. Make this a little longer. Okay. So now what we could do is, if we look at our equation, which is if the summation x is k is equal to 0 to infinity, 1 minus x. Oh, sorry. X to the power of k is equal to 1 over 1 minus x. If we substitute this x with 5x to the power of 5, right, then we just need to substitute this with 5x to the power of 5, right? So technically, this thing is the same thing as saying 5 times the summation of k is equal to 0 to infinity of, let's write the parentheses so it looks a little bit more organized. So 1 minus 5x to the power of 5, which is just this 1 over 1 minus 5x to the power 5, is just equal to this. So it's the summation of 5x to the power 5 to the power of k, right? And if you want to simplify it even further, you could just say the summation is k is equal to 0, infinity, and you can multiply the 5 back in. So this is just 5 to the power times 5 to power times x to the power 5 to the power of k. So this k distributes to the 5 and the x to the power 5. So that's just 5k. And then you multiply that 5 in, so you just add that 1. And then you multiply by x to 5k. So it's just equivalent. So this is your power series representation for your function 5 over 1 minus 5 to 1 minus 5x to the power 5. If if right, because we have this general formula, the x has to be between -1 and 1, right? All you have to do is just modify it, right? Because x has to be -1 and 1, so x 5, because we substitute x with 5x to the power 5. So 5x to the power 5 has to be less than -1 to 1. So you just, oops, 1 to 1, right? So you just divide 5 to both sides, so -1 divided by 5 is less than x to the power 5 is less than 1 over 5. Then you take the fifth root of the, so we just take the fifth root of both of these, so it's the fifth root of -1 divided by 5 is less than x is less than the fifth root of 1 over 5, right? And that's basically it. And that's all you have to do. So the x for so the power series from k is equal to 0 to infinity of 5 to the power of k plus 1 times x to the power of 5k. If x is between the fifth root of -1 over 5 to the fifth root of 1 over 5, then this equation is going to be the same thing as this equation. And that's a general idea of how to represent like a function as a power series. So let's kind of understand this with another example. So let's say f of x is equal to x to the power of 5 divided by 1 minus x, right? So we know that our summation of k is equal to 0 to infinity of x to the power of k is equal to 1 over 1 minus x, right? So what we could have is that since this is the same thing, if we distribute out the x5, right? x5 times 1 over 1 minus x. Okay, so you could plug in this equation in. So x to the power of 5 times the summation of k is equal to 0, infinity, as a x to the power of k, right? And now all you have to do is that you could just, if you think about what this kind of represents, you just plug in k is equal to 0, right? So that's k is equal to 0, so x power 0 is 1, put that parentheses, plus when k is equal to 1, that's x. When k is equal to 2, that's x to the power of 2. When k is equal to 3, that's x to the power of 3, etc., 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 right? That's what the summation is equal to, and we have to multiply that to x is equal to 5. So that's the same thing as x to the power of 5. Oops, sorry. X to the power of 5 times 1 is just x to the power of 5. X to the power of 5 times x is just x to the power of 6. X to the power of 5 times x to the power of 2 is x to the power of 7, and etc., right? Right. So this is the pattern. So now we could just rewrite this as a summation. So what we could do, kind of delete all this, right? So this f of x, which is equal to x to the power of 5 over 1 minus x, this could be rewritten as the summation. Oops, sorry. Okay. We can take this as the summation as x, sorry, summation as k is equal to 5, and we have to go to infinity, of x to the power of k. right? And that's basically all it is, right? And since all we had was this is the summation of k is equal to 0, infinity of x to the power of k, which is just from -1 to where the x is just -1 to 1. Since this negative, since this x to the 5 is outside, it doesn't matter. So then all we have is, or you could just plug it back in, because if that's x to the power of 5 is less than -1 and 1, right? It's still from -1 to 1. So it doesn't really matter. Because if you take the fifth root of -1, that's just -1. Take the fifth root of 1, that's just 1. So that means this equation is the same as this equation, but in just summation form. Okay. Now let's try a more challenging example. So let's say we have f of x, and that is equal to the inverse tan of x, right? So we want to find the equate the power series version of this equation. So for functions like these, where we can initially see where the like 1 over 1 minus x is, what we could do to look at it is that we could always look at the derivative. So how this works is that we know that the derivative, if you search it up in the internet or so, if you could prove it, doesn't matter which way you find what the derivative of the inverse tan is. If you take the derivative of that, that is 1 over 1 plus x squared, which you can search up on the internet if you want. So using this idea, we just kind of see something of 1 over 1 minus x, right? We could see some kind of resemblance. Now we just need to get into that form. So what we have is that we can have the summation of k is equal to 0 to infinity, right? But of x to the power of k is equal to 1 over 1 minus x, right? So if we substitute x is equal to negative x squared into this equation, right? Then that would just be equal to 1 over 1 negative x squared into this x, so that's plus x squared. So this is the same thing as this equation, right? So we know that if we substitute that in, okay, let's kind of delete this. We know that the derivative of f is equal to the summation as k is equal to 0 of infinity of, since we substitute x with negative k, negative x to the power of 2, right, to get 1 over x plus 2 is equal to k. So we know that this is true. Let's kind of make this a little nicer to look at. Negative x to the power of 2 power of k. Okay, so now we could kind of rewrite this to simplify this a little bit better. We could say this is the summation as k is equal to 0 to infinity, and that's just -1 to the power of k, right? We just distribute out the k to the -1 here, and then k to the x to the power of 2x. So it's multiplied by x to the power of 2x. So it just looks a little bit nicer. Okay, so we know that this is the derivative, right? So we don't want the power series of the derivative. We want the power series of the original functions. So to find the original function of a power series, all we have to do is just to take the integral, right? Because if we take the integral of a derivative, we just get back the actual function. So we just need to take the integral of this. So how do we take the integral of this? Well, all we have to do is just find like a shorter, find a more like concise equation, and then kind of like reverse back. So let's plug in some values for k. So when k is equal to 0, we have -1 to the power of 0 is 1, and x to the power of 2 times 0 is 1, right? So 1 times 1 is 1, right? So we know that that's 1 plus. Now, if k is equal to 1 now, -1 to the power of 1, that's -1, and x to the power of 2, that's just 2. So x2 times this negative 1 is negative x squared. So negative x squared plus, when k is equal to 2 now. So when k is equal to 2, that's negative 1 to the power 2. That's positive. So we have x to the power 4. So this is x to the power 4. Okay. So plus x to the power 4. Plus, when k is equal to 3, right? That's got to be negative x to the power 6. So this is negative x to the power 6. So we're kind of seeing a pattern, right? So let's say k is equal to 4 now. And let's just stop there afterwards. So negative 1 to the power 4 is positive. X to the power 2 times 4 is x to the power 8. So that's x plus x to the power 8. Okay. So let's kind of delete all this because we don't need it. And let's kind of move all this to the top. Okay. So do we see a pattern here? It's 1 and then x squared, then x fourth to x6 to x8, right? So we could rewrite this as the summation. So actually, never mind. Sorry about that. This is still the derivative, right? Because I'm just rewriting this equation. I'm just expanding this summation out into its basic terms, right? And this goes on for infinity. Oops, sorry about that. And this goes on for infinity of adding, right? Of more terms. So this is the derivative. So to get the integral, we just have to take, the like a reverse, a antiderivative, right? As an integral. So what derivative of a derivative of what function is equal to 1? Well, the derivative of that is just x, right? Derivative of x is equal to 1, right? Now, how do we get x squared, negative x squared? Well, we just had to 3 and then negative, right? So the derivative of negative 1/3 x to the power 3 is just negative x to power squared, right? Now, how do we get a derivative of this? Well, that's x to the power 5, and then you put 1 over 5. Derivative of this, 5 times 1 over 5 is 1, so it gets that coefficient of 1, and then minus 1, so x to the power 4. So this is the right derivative, right? I mean, this is the right integral. So the integral of this is equal to x to 4. The derivative of 1 over x to the power 5 is x to the power 4. Okay, now the integral of negative x to the power 6 is just x to the power 7, negative 1 over 7, right? Plus, and then this one is just x to the power 9 and 1 over 9. And then etc., etc., you know. So now we just had, since this is the integral of this, that means this as a summation as a power series is the integral of this equation, which is just f of x, which is what we want, right? So we just have to find the summation of this, which would be the power series of our actual function, of our tangent, inverse tangent of x. So we could rewrite that as the summation as k is equal to 0, right? And we could go into infinity because it always goes to infinity, right? So since it's alternating between negative and positive, right, we have to put a negative 1 somewhere. And since it begins with a positive, we could just put a k here. Because because for every single odd number, so the first term, the third term, the fifth term, they're all odd. All these odd are positive, so we just put a 0 in here. And if so, the first, which is 0, the second, and the fourth, they're all positive. And then we're gonna add, and then we're gonna multiply to make sure that these terms stay constant, right? So they're increasing by 2 every single order, so that's just 2k. And since it starts at 0, this is the first one, so you have to plus 1. Actually, plus 3, right? This is the 0, this is the 1. So plug in 1, that's a 3, and then plug in 2, that's a 4, that's a 5, right? And then you have x times x to the power of 2k plus 3, right? Let's see if this makes sense. If k is equal to 0, that's negative 1. That's uh that's 1 out of 3. Actually, oops. Sorry, this is a 1. Oops. Plus 1 times 2 times x to the power of 2x plus 1. So we could just check if this is true. So if k is equal to 0, then that's negative 1 to 0 is 1. And then you plug in a 0 here. So that's just 2 times 0 is 0 plus 1. So that's also 1. So this is 1, this is 1. And this is x. So this is true. And when x is equal to 1, that's negative 1. This is 3, so this is negative 1/3. And then this is negative 1/3 x cubed. Now, when k is equal to 2, that's positive. That's a 5. That's 1 over 5. So that's x equals 1 over 5 times x over 5. So this is the summation of this entire equation. So this is the power series of in the inverse tangent, uh, the inverse tangent. So of our function, right? So that is basically the general idea of how to find a power series of a function if you want to find the power series, basically. So you just use the infinite geometric series, which is the summation as k is equal to 0, as equal to infinity, of x to the power of k, where k, where x has to be between 1 and negative 1. This sum is equal to 1 over 1 minus x. And you have to just put it in that term. And you have to find the similar version of where we could plug it in. And then if you need something like 1 over 1 minus x squared, just plug in x squared into this x. So then this would become 1 over 1 minus x squared. So then you could substitute it in. And that's the general idea of power series. Thanks for watching, and I'll see you at the next math record.